Okie dokie, let's do this. Hello, everyone. How are you doing? How's the transmission? Am I clear? Am I audible? Am I visible? Excellent. Welcome to another MySound webinar. Let's get started by looking at the usual household notes first, which means that I'm going to share my screen. And there we go. Okay. So, like I said, welcome to another MySound webinar. Today is going to be all about low-mid beam control. Very interesting topic, if I say so myself. But before diving off the deep end, let's talk a little bit about our video communication platform first. We're using Zoom, as always, and that means that in front of you, you're expected to see a window not unlike the one you have in front of you right now. If you would like to see who else is joining you on today's call, please click on the participants button, in which case a window shows to the right side pops up, showing you your fellow attendees on today's call. Now, we encourage you to ask questions also during the session, but in order to do so in an organized fashion, we would like you to make use of the so-called raise hand feature. Notice that in the bottom right corner, there is a button called raise hand, and whenever you click that button, a blue hand icon pops up in the corner of my eye, informing me that you are about to ask a question. Now, in order to ask the question itself, we encourage you to make use of the chat feature. So, whenever you click on the chat balloon icon, the right-hand window will split in half, bringing up a new dialog and a field where you can enter a message. If you would like to address everyone on the call, it's set to everyone by default. However, if you should happen to see a friend or family member or colleague, then you can also message that person in private. So far, so good. Okay. The other thing to point out is that we're simulcasting, as always, through our user community Facebook group. That means that welcome to you as well. The group is growing steadily, over 8,850 members, 8,850 members. So welcome to you as well. This is going to be about LMBC, which is, of course, part of the tool set, as we're about to discover. But that being said, in order to get the most out of today's webinar, it helps if you're familiar with Compass. So in order to get up and running with Compass, for those that are not familiar with our control software, please watch the Introduction to Compass webinar. Same goes for MapXT. We will be looking at two designs in MapXT. For those that are new to MapXT, please watch the Introduction to MapXT webinar upon conclusion of today's webinar to learn more about MapXT. And then the auto splay webinar, because today's arrays will already have been splayed and aimed properly. And that means that we're not going to go through those steps. We're going to look at a stage which is pretty advanced in terms of arrays already deployed and splayed. So if you want to know more about how to get there, how to splay your array, be sure to watch the auto splay webinar. All these webinars can be found on our YouTube channel, Thinking Sound, to which you find the link in front of you as we speak right now. That's where you will find those webinars, including many, many more webinars that we've conducted during the past 8 weeks. LMBC is a feature of the Galaxy platform, the Galileo Galaxy Devices platform, and can be controlled from Compass and can be controlled from Compass Go, as we learned during the Compass Go webinar. We've mentioned it already several times, but now the time has come to actually start looking at what is low mid beam control, what is LMBC, and what will it do. And I like it a great deal because it's one of those textbook examples which shows you that you cannot beat physics, and hopefully that will become more clear during the course of today's webinar. So I made my checklist, I got my pen ready, and that means that what I intend to cover today is what is low mid beam control, a little bit about the scientific literature, because what we're about to explore has been known for quite some time. In order to appreciate what is going on, we should definitely look at the vertical coverage that is inherent to a single line array element, not to be mistaken for a point source. Then we're going to talk about how we can use multiple of those elements in what is known as colloquially a line array, where we can then introduce control by committee. So by organizing our line array elements in a careful and delicate way, we can achieve control by committee for the vast majority of audible frequencies, except, well, not all frequencies as we're about to discover, but we're going to get into that soon. Because when we try to introduce control by committee, there's basically two regimes or two principles that we resort to. There's the phase steering, which is all about narrowing the beam, and then there's the amplitude steering, which is all about spreading the beam. It's point and shoot, sending the sound where we need it to go. And we need to understand those two regimes that are at play when we work with line arrays trying to achieve control by committee, a committee of line array elements. Then we're going to look at an example of a beam spread, and we'll come to the conclusion that without bells and whistles, that for certain frequencies, the beam will end up being too narrow. And many attempts have been made at trying to address this, at trying to improve this, at trying to fix this. And what I like to do is, rather than going through each and every one of those possible solutions, what I like to do is look at the root cause for the issue at hand, because if you understand the root cause, then it basically eliminates all other solutions that have been tried in the past, or all other solutions that come to mind. If you understand the root cause, then it becomes readily apparent that there's only one way that this can be or one way, or I should say that there's only one domain where this can be fixed. So we're going to talk about the root cause. Because once we understand the root cause, you see that the next bullet point in my checklist is solutions. Well, it's not going to be EQ, as we're about to discover. Then once we've had our first encounter with LMBC, we're going to look at an example of a steer up application. And then finally, once we looked at what we can gain with LMBC, what we can achieve with LMBC, then we'll finish with an exploration of how to actually set it up in Compass. And to finish, there is a function which is known as the global all-pass filter, and that is something that we'll discover at the last possible moment. So that's my checklist for today. I hope it will be as enjoyable to you as it is to me. And that means that without further ado, what is low mid beam control? Low mid beam control is basically a tool for Galaxy users that allows us to modify the natural vertical coverage of the low mid frequencies in a Meyer sound curvilinear array to more closely match the high frequency coverage. So it's a lot about beam width. Beam width is one of those terms that we use to indicate the vertical coverage angle of an array. What is the beam width of the entire array? So that is what low mid beam control allows us to do. It allows us to match the beam width of the low mids and have them match better those of the mid and high frequencies. Sounds maybe like an abstract at this point, but rest assured, hopefully by the course of this webinar, it will become more clear why there is room for improvement and how to achieve that. But you have to realize that line array theory is mature. It's mature. It's been around for quite some time now. This is a very famous book by Harry Olson. And Harry Olson in 1940, which is at the outbreak of the Second World War, in 1940, Harry Olson already wrote about straight line source behavior and curved line source behavior, including the math, the equations that describe the behavior of line sources, whether the line sources are continuous or whether the line sources are made out of discrete steps, discrete point sources living on a string on the line. This has been known for quite some time. And the same is true for tilting the beam by means of phase shift. In 1957, the same Harry Olson, in another book of his, already wrote about how to beam tilt by means of phase shift. So what we're about to look at is not new. It's not novel. It's mature. It's been around for decades, quite literally, so to speak. And that means that the first thing that I'd like to do with you is start by investigating the coverage of a single line array element. So we're going to look at a leopard line array element. We're going to look at a section view. And for those that have watched the other webinars by now, you hopefully understand what we mean by section view. We're going to look at a cross section, which means that we have a single element living in our prediction plane. And we're going to look at several frequencies and see how the vertical coverage angle of a single element changes over frequency. So the first frequency that we will look at is 125 hertz. So here you see a single leopard element living over here all by itself, completely alone. We're looking at 125 hertz, and it suffices to say that a single leopard at 125 hertz is omnidirectional. We've discussed this also during previous webinars. Once the source is very small in comparison to the wavelengths that it's reproducing, then all sources tend to become omnidirectional. So at 125 hertz, we're talking about 3 meters, give or take. And suffices to say that a leopard is very small by the time that you're reproducing 3-meter wavelengths. So the leopard is virtually omnidirectional at those frequencies, which typically goes for any loudspeaker by the time you get that low, including a loudspeaker as large as Leo. Once you go low enough, all loudspeakers tend to become omnidirectional because the wavelengths that they're reproducing are orders of magnitude larger than their own physical dimensions. However, if we go up in frequency by an octave, now we actually measure a coverage angle. And for those that remember, when we define a coverage angle, we're saying, okay, what is the angle with respect to the loudspeaker? What is the angle with respect to the loudspeaker where we observe 6 decibels of angular attenuation? So we've looked at this in previous webinars, such as the down tilt translation webinar. So I'm gonna not explain at great length once more how to measure a coverage angle. Suffices to say that at 250 hertz, a single leopard is still well over hemispherical, well over 180 degrees of vertical coverage, mind you. Let's go up by another octave. By now we're at 500 hertz, and now you clearly start to see that the leopard is becoming narrower. It's becoming more beamy, for lack of a description. This is a single element, and by the time you're at 500 hertz, between the -6 dB points, has now shrunk to 140 degrees. Let's go up by one more octave. Now we are at 1 kilohertz, and also at 1 kilohertz, you see that the beam has become more narrow. Around 1 kilohertz, a single leopard is now about 100 degrees. Let's go up by another octave, and again, history repeated itself, and the leopard started to become progressively more narrow. Come 2 kilohertz, it's now only 46 degrees of vertical coverage. At 4 kilohertz, that value has essentially been cut in half, and at 4 kilohertz, we see a vertical coverage angle of 32 degrees. At 8 kilohertz, it shrunk even further. At 8 kilohertz, we're looking at 16 degrees of vertical coverage. And by the time we come to 16 kilohertz, our leopard loudspeaker is now so narrow. This is what I call, this is essentially a laser beam, if you will. It's become so narrow at 16 kilohertz that its vertical coverage angle between the -6 dB points has shrunk to 10 degrees. The important takeaway is that our leopard loudspeaker, or any other line array element for that matter, in the vertical, mind you, we're not talking about the horizontal plane, but in the vertical, line array elements do not exhibit the same vertical coverage angle for more than a single frequency. After all, 10 degrees at 16 kilohertz, 16 degrees at 8 kilohertz, 32 degrees at 4 kilohertz, 64 degrees at 2 kilohertz, 100 degrees at 1 kilohertz, 140 degrees at 500 hertz, 250 hertz, 180 degrees, and then it ends up being omnidirectional. Not a single frequency features the same coverage angle as we see in these couple of slides. So if we were to plot all those coverage angles in a chart against frequency, then we get what is known as a beam width plot. So in the top of the screen over here, you see a beam width plot, frequency running from left to right. and the vertical coverage angle, now referred to as the beam width, shown top to bottom. So my frequencies run left to right, but my beam width runs top to bottom, where 360 degrees of beam width means that you're omnidirectional. And notice that below 200 hertz or so, this is an illustration. This is based on an actual measurement, but it's been made to look more simple to convey the abstraction. That being said, it's in perfectly good agreement with actual measurements. But what you see is that below 200 hertz, the Lambert element, or any other line array element for that matter, is omnidirectional. Now, if you have a LINA, that milestone where it becomes omnidirectional, when you have a LINA, this milestone might shift up in frequency, whereas if you have a LEO, it might shift down in frequency, but ultimately all of these loudspeakers, depending on their size, will end up becoming omnidirectional. Now, as we go up in frequency, you see that the vertical beam, the coverage angle as a function of frequency, that the coverage angle becomes narrower and narrower and narrower and narrower and narrower and narrower and narrower to the point that you get your 10 degrees or so come 16 kilohertz. And this behavior is known as proportional Q. Why is it known as proportional Q? Because as we go up in frequency, our single line array element starts to become narrower and narrower and narrower. And for those of you that are familiar with Q, as in directivity factor, then you know that as loudspeakers become narrower, the Q value rises. So a very narrow loudspeaker is high Q, whereas an omnidirectional loudspeaker is low Q. So that's why this is called proportional Q, because Q rises in proportion to frequency. As frequency goes up, the loudspeaker becomes narrower, and therefore its directivity factor, its Q value goes up, hence proportional Q. And this is what makes every line array element in the vertical, mind you, a tick. They're omnidirectional at low frequencies, and then they become super directional at high frequencies, not showing you the same beam width for more than a single frequency. And this is the building block. This is the building block that we now need to use in such a way that we can string them together, constructing a line array, a curvilinear array while making a line array out of it, and somehow arrange those elements within a line array to achieve control by committee, okay, to achieve a desired coverage pattern by committee, using a loudspeaker that is omnidirectional in the low end and very directional at high frequencies. And that means that we need to leverage two mechanisms. We need to leverage two mechanisms against each other to pull that off. Because at low frequencies, we have loudspeakers that are omnidirectional, and at high frequencies, we have loudspeakers that have become very directional. And that means that at low frequencies, we're going to resort to a regime which you can think of as phase steering. Why do we need to resort to phase steering? Because the loudspeakers themselves, as part of an array, are omnidirectional or near omnidirectional. They're low Q. And that means that even if you have an array of 12 to 14 or 16 loudspeakers, that at low frequencies, all audience members live in the shared custody of all these low frequency transducers. If they're omnidirectional, they cannot steer clear from each other's territory. So at low frequencies, we're in the joint custody of all these omnidirectional elements in that frequency range, mind you. If you're omnidirectional, if you're a loudspeaker and you're omnidirectional, then a single element is what I like to say is immune to splay. If you rotate an omnidirectional loudspeaker, it will not change its amplitude in whatever direction it is sending. If that loudspeaker is looking you in the face or is looking away from you, if it's omnidirectional, it's not expected to make a major change in amplitude. That's to say, the amplitude that you're perceiving. So that makes the loudspeaker, basically renders it immune to splay in terms of amplitude. That being said, we're still going to use that loudspeaker to narrow the beam. And in order to do so, what is the driving force, the driver at low frequencies, is the length and the shape of the array. As we're about to discover, the longer the array is, the more the beam gets narrowed, the more the beam gets squashed, whereas as shorter the array is, the more the beams get spread, or the beam, singular, gets spread. So that is a phase steering. That is the driving mechanism at low frequencies where we have to rely on phase steering because the loudspeakers are still omnidirectional. Now, as we start to go up in frequency, our single line array element starts to become narrower and narrower and narrower to the point that it becomes the ultimate point and shoot loudspeaker. I mean, seriously, by the time you're at 16 kilohertz with 10 degrees of vertical coverage, that's a laser. If you want that to go to the third balcony, all you have to do is send it there. If you want it to go to the first row, all you have to do is send it there. So by the time you get to 16 kilohertz, it becomes the ultimate point and shoot loudspeaker. So the mechanism or regime that is at play at high frequencies is what we refer to as amplitude steering, because now the loudspeakers have become very directional. Also means that they're super sensitive to splay. I mean, with only 10 degrees of vertical coverage comes 16 kilohertz. If your angle is off by 10 degrees, you're basically out of the coverage at 16 kilohertz to that particular loudspeaker. So now our loudspeaker becomes very sensitive to display between adjacent elements. And that means that now, using point and shoot, we can send the sound where we want it to go, literally by aiming the loudspeakers there. And the challenge becomes to balance these two regimes, to leverage these two regimes, phase steering as a function of array length and shape, against amplitude steering, where it ultimately becomes point and shoot. Now, I want to show you both mechanisms. We do not have nearly enough time to discuss the entire inner workings of line arrays, but this will give you enough insight to become dangerous, as they say. So let's look at phase steering first. Specifically, the beam narrowing as a function of line length. So let's use an MM4. An MM4 is arguably the smallest loudspeaker that we built. It is about 10 centimeters tall, 10 centimeters wide. It's a single transducer. And we're going to look at a frequency of 1 kilohertz. And now you might say, well, 1 kilohertz, that's not particularly low in frequency. Sure, but this is still a very small loudspeaker. After all, if you're 1 kilohertz, then one wavelength is about 1 foot, or 34 centimeters, give or take. And that means that a 1 kilohertz wavelength is 3 times taller than our loudspeaker, which still makes our loudspeaker small by comparison. And if you look on the right side where you see a section view, a prediction at 1 kilohertz of a single MM4 XP, then you see that it's still well over hemispherical. It might not be entirely omnidirectional anymore, but it's still well over hemispherical. So it's all about proportions. You always have to think in terms of what is the size of my source with respect to the wavelengths that it's reproducing. And even at 1 kilohertz, this small loudspeaker is still 3 times smaller than a 1 kilohertz wavelength. So let's look at the section view. Now notice that here you see a string of 19 MM4s, but we're not looking at a prediction of all 19 MM4s, because if you look at the text below, you see that only one element has been soloed out of these 19 element string. So we do see the entire array, but the only loudspeaker which is producing any audible sound is the loudspeaker in the middle. All the other ones have been muted. And just to get that across, that's why we have in the bottom, we have in fat letters saying that even though you see a string of 19 elements, only one is currently turned on, and that's the one that has been soloed. And notice that at 1 kilohertz, that my MM4XP is 3 times smaller, roughly 3 times smaller than a 1 kilohertz wavelength. So the length of the array, well, I wouldn't call it array, it's one loudspeaker, but strictly speaking, the length of the array is 3 times or 3 of a tenth, 1/3 of a 1 kilohertz wavelength. And well, it's it's not omnidirectional, but it's well over hemispherical. Now watch what happens if we turn on the adjacent loudspeakers. So not only just the one in the center, which we're looking at right now, the one in the center, but also its neighbors, the one living on top of it and the one living below it. Let's see what happens with our beam when we turn on the neighbors to my single MM4XP. So here we go. Let's add 2 more loudspeakers. By now, we're looking still at the same frequency, 1 kilohertz, but rather than seeing 1 MM4, that's to say 1 active MM4, we now see 3 active MM4s. And notice that as we went from 1 to 3, suffices to say that the beam became narrower. And by the beam, we of course mean the vertical coverage angle of the beam that became narrower. This is what we're trying to get across. By now, the length of my array, well, a single MM4 is 10 centimeters. 3 of those, therefore, are 30 centimeters, almost 1 foot. So 3 of these MM10s is about the same size as 1 wavelength of 1 kilohertz. And you clearly see that the beam became narrower. Let's add 2 more elements, which means that if we go to the next slide, that now my array of active MM4s is currently 5 elements. And that means that the array is now actually, with 5 elements, is about 1.5 times longer than the frequency that's reproducing. And again, you can see that as we went from 3 to 5, that it became narrower. Let's add 2 more elements. That means that our array now consists of 7 active MM4s, making for the active part of the array is now 2.1 times longer than my wavelength. And again, you can clearly see that it became narrower as we went from 5 to 7 elements. And every time we turn on more elements, going to 9, going to 11, going to 13, going to 15, going to 17, and ultimately going to 19, now for the first time, all 19 MM4s are activated within the 19 MM4 array. Without exception, you see that as our line gets longer, as we start to activate more MM4s, the line longer, that the beam became narrower. And that is all due to phase steering, where you see that the narrowing of the beam is a function of the length of the beam. And that is the driving mechanism at low frequencies for line arrays. It is the line length which dictates the width of the beam in the vertical at low frequencies. If we go back to one element, again, well over hemispherical, but every time we add more elements, making the line effectively longer, you clearly see the beam being narrowed, the beam being squashed as a function of line length. So that is what's going on at low frequencies. Now, if we go to mid and high frequencies, where our individual line array elements start to become very directional to the point that they are a laser with 10 degrees at 16 kilohertz, give or take, now it becomes an exercise in point and shoot. And basically, we've already discussed this during the auto splay webinar. Because if I take 16 Lion loudspeakers with half of a degree splay, then at this point, it's clear that we're sending too much energy to the second half of the venue while overshooting the start of the audience. This is again section view, and it suffices to say that we're pointing the loudspeakers in the wrong direction. However, at 4 kilohertz, I can set my splays in such a way, as we discussed in the auto splay webinar, I can set my splays in such a way that we end up sending the sound where it needs to go. So now, if we start to fan out our array, we basically see the effect of amplitude steering, because every time that we open up the array more and more and more and more, you notice that once we start sending the loudspeakers in the right direction, that our level distribution from first to last row starts to even out. Of course, by the time that we're done, for those that watch the auto splay webinar, they can tell that in the top we have less splay between adjacent elements, whereas in the bottom we have more splay between adjacent elements, because the only way that we can overcome what is now known as the range ratio, which is the range ratio from loudspeaker to last row with respect to array to first row, the only way that we can overcome that range ratio, that we can throw further, is to have a team effort going to the going to the last row, whereas in the first row, the solo effort suffices. I don't need the combined horsepower of 16 loudspeakers in the first row. So by deliberately increasing the splay between adjacent loudspeakers, we reduce the team effort to the point that it becomes a solo effort because I don't need the combined horsepower in the first row. This is everything that we already discussed in the auto splay webinar, and you clearly see that the driving mechanism over here is the inter-element splay angle, which allows us to steer the sound where we want it to go. So at mid and high frequencies, it is the splay between the loudspeakers that determines whether the sound ends up at the right point in space, that is to say at our ears and not on the plaster. But at low frequencies, it is the length of the line and the shape, as we're about to discover, which primarily dictates the behavior of the beam at low frequencies. Okay, so that being said, let's look at an example where LMBC could produce a solution known as a beam spread, which means that I'm going to quit the keynote. That is to say, I'm going to abandon the keynote, and this will be today's first example. For those that have been watching the Lena in a House of Worship webinar, surely this venue will look familiar to you by now. The only thing that is different is that this time I'm not using Lenas. This time I'm using leopards. I've set auto splay, making sure that we have good coverage for the majority of the audience. And that means that let's do a 4 kilohertz prediction and see what we have. So at 4 kilohertz, I'm completely happy for reasons that we've discussed before. Everybody is living within 6 dB of level variance or less. So at 4 kilohertz, this looks very promising. Let's go to 2 kilohertz, which is still mid-high frequencies. Let's go to 2 kilohertz. Also 2 kilohertz looks very promising. So at mid and high frequencies, using amplitude steering, sending the sound where it needs to go, okay, all of our needs have been taken care of by simply properly pointing and shooting the loudspeakers. Now let's go to very low frequencies. Let's look at very low frequencies. Let's go to 63 hertz. 63 hertz is about the bottom edge of the frequency range of a leopard system, give or take. And this is the coverage at 63 hertz. And again, that looks reasonably well. If I start counting colors, starting over here, which is the start of coverage, where we have this green color, and then we go into this lime color, and then we go into this blue color. Well, that's 2 color divisions. That is 6 dB of variance front to back. Not unlike what we see at 4 kilohertz. At 4 kilohertz, we also see 6 dB of variance front to back. Of course, the beam is less defined over here because we have longer wavelengths, but at 4 kilohertz, the beam has sharper edges because the elements themselves are now much narrower. But, at 63 hertz and at 4 kilohertz, we see about 6 dB of variance front to back, also at 2 kilohertz. So many frequencies are already taken care of. Let's go back to 63. But rather than looking at an entire octave, I want to go a little bit more narrow band. So I instructed MAP to show me 1/3 octave rather than 1 octave. And let's go to 63 hertz and only look at 1/3. Well, we've seen that before. Okay, that's 63 hertz. Let's go up in frequency. Let's go to 80 hertz. Okay, 80 hertz. If I pay careful attention, it appeared as if it became a little bit narrower. Interesting. Let's keep track of that. Let's go to 100 hertz. At 100 hertz, might have been my imagination, but it looked like it became even more narrow. Let's go to 125 hertz. At 125 hertz, it's definitely narrower. Let's go to 160 hertz. This is 160 hertz. Wow. Even more narrow, even more defined. Let's go to 200 hertz. Okay, and at 200 hertz, wow. Compare this picture at 200 hertz and compare this picture to what happens at 63 hertz. This beam is substantially wider, whereas by the time we get to 200 hertz, this beam is substantially narrower. But by the time, we go to the mid and high frequencies, which we already checked out, we know that that beam opens up again as a function of amplitude steering, as a function of point and shoot. But around 200 hertz, it suffices to say that this beam is essentially too narrow. I mean, look at it. It touches down. If we draw a line through our beam, it's pointing somewhere at the fourth row underneath the balcony. That is the general direction of that beam. And as we abandon that area, we actually start to lose level. So now for the first time in your life, things actually became softer as you start to approach the stage. Whereas normally it's the other way around. If you start to approach the stage, things tend to get louder. And the same is true when we go up to the balcony. If we go up to the balcony, we also see an attenuation according to the scale. So we have a beam which is too narrow. It's overshooting the first part of the audience, the first couple of rows. Then it's doing a nosedive under the balcony, and it's too narrow to have any substantial contribution on the balcony. And this is the problem that we're dealing with. This is basically your phase steering, your line length, which is the driving force at low frequencies, is doing too much of a good thing, as we're about to discover. And then if we go up in frequency, then ultimately this beam will open up once more. Let's continue. Let's go to 250. Okay. Let's go to 315. Let's go to 400. Now you start to see that the beam progressively starts to become wider again, because we're leaving the regime where the line length and shape are the driving force, and we're crossing into the regime where amplitude steering, point and shoot starts to work in our favor. And as we go up in frequency, you clearly see that the beam starts to open up once more. And if we were to rewind, going down in frequency again, you see that the beam starts to contract once more, starts to become narrower. And that means that at those low mid frequencies, the shape of our beam is not the same as it is at very low frequencies, at mid and high frequencies, where we are in the sole custody of the ribbon emulation manifold waveguides that allow us to send the sound where it needs to go. Now, there is an interesting thing that I would like to point out to you, which is that the orientation of this beam is always perpendicular to the overall orientation of the array. Let me hide the center lines for a while and bring up a tool which some of you might have seen me use before, which is Pixel Stick. Pixel Stick allows you to measure the distance between two pixels on your screen. But what it allows me to do is put one point at the origin of the array and the other point along the general direction of the beam. And if we do that carefully, then hopefully by now you should be able to appreciate that the general direction of this beam is completely perpendicular to the orientation of the array as a whole. So if I were to draw a cross along Pixel Stick, then hopefully everybody is able to appreciate that this runs perpendicular to the array as a whole at a 90-degree angle. And that's always the case for that concentrated beam of energy. At these low frequencies, where the loudspeakers barely stop being omnidirectional, the orientation of that beam is always perpendicular at a 90-degree angle to the array as a whole. 90 degree angle to the array as a whole. And that is something that you will always see time and again once you start to look for this behavior. So now we need to discuss, why does this happen? Why is the beam so narrow, and why is it overshooting the start of the audience, making a nosedive underneath the balcony, And more important, what can we do about it? What can we do to change this? Because I've also put some microphones in this project, and let me unhide those microphones. And here we see the 3 microphones that I used in this project. Now, for those that are now familiar with our naming convention, this is V top, that is the top, the vertical top of coverage. This is V bottom, which is the start of coverage. And because this microphone is staring the array in the face, so to speak, I've called that position on axis in the measurements that we're about to see. So let's call this V top, which we've done on more than one occasion. Let's call this the on X position, and let's call this the V bottom position. And let's see whether our 3 transfer functions, our 3 measurements, confirm the same trend that we already see here in map. In order to show you that, I want to go to that particular slide, because we already saw in map that our beam is too narrow. It's doing an overshoot of the first couple of rows. It's doing a nosedive, landing underneath the balcony, and then it's missing basically the people on top of the balcony. And let's see whether our transfer functions confirm that. And the answer is yes. So for your understanding, the blue trace is the measurement at the first row in the vertical bottom, which is the start of coverage. The orange line is the microphone on top of the last row on top of the balcony. But it's the blue line which is our microphone underneath the balcony. And it's clear to say that under the balcony, there is a concentration of low-mid frequencies. We have uniformity above 1K because the imaginary line over the peaks shows the same trend. We also have uniformity at 63 Hertz, which we already predicted. So below 100 Hertz, all frequencies attenuate at the same rate over distance, and above 1 kilohertz, all frequencies attenuate at the same rate over distance, and that's how you preserve tonality. If all frequencies lose the same amount of decibels over distance, then tonality is preserved. But from our 3 measurements, first row, on axis, and last row, we can see that under the balcony, those low-mid frequencies are louder than in the start of our audience and in the end of our audience. And that is that beam that is overshooting the first row, which you can clearly see from the measurement, and doing a nosedive underneath the balcony, never making it to on top of the balcony. So the challenge becomes, how can we spread the beam? Because the beam is at this point, the beam is too narrow. And before we're going to look at the solution, I first want to point out that this is already known in 1940. In 1940, Harry Olsen already describes the behavior of curved line sources or curvilinear sources. And in 1940, he already showed in his book that if we look at a section view of an array, over here we have an array. This is an 11-speaker leopard array. It's living over here. We're looking at a section view. In 1940, Harry Olsen already predicted that the expected vertical coverage angle approximates this slice of pizza. So I just drew a slice of pizza, section view, and in 1940, Harry Olsen already wrote that the expected vertical coverage angle approximates that slice of pizza. Well, let's see whether this is true by going to the next slide. In the top left corner, we see our array at 63 Hertz. And if we start looking for 6 decibels of attenuation, then it's outside of the plot. Okay, so that means that at 63 Hertz, our leopard array, our 11-box leopard array in this example is way wider than the predicted slice of pizza. But as we go up 1 octave in frequency, then we actually can identify our -6 dB points, and we notice that the beam has become narrower because now line length, the length of the array, starts to do its thing. And then for the same 11-box hang, we actually see that around 250 Hertz, our -6 dB point actually live within the slice of pizza. This is that same frequency range, give or take. It's a function of the length and shape of the array. But notice that since this is also an 11 box leopard array, that around 250 hertz, this beam is actually narrower than the promised slice of pizza. But then as you go up in frequency once more at 500 hertz, abandoning the regime where line length and shape are the driving force, the loudspeakers are omnidirectional, starting to progress into that part of the spectrum where the loudspeakers become highly directional, become point and shoot, then you see that the beam opens up again because we're sending the sound where we want it to go. And at 1 kilohertz, you also see that the beam width starts to conform with that slice of pizza. And from 2 kilohertz, 4 kilohertz, 8 kilohertz and up, it's essentially that slice of pizza which was already predicted in 1940. That being said, there is this in-between frequency span where the beam ends up being a little bit too narrow, where before it opens up again as a function of the amplitude steering of the point and shoot. And we also see exactly that same challenge with our real array in the map file. We see that same problem, in this case, around the same frequency because the arrays are of similar make and model and of similar dimensions. So now the question becomes, if this is physics throwing you a curveball, and that's what I like about it, this is physics, okay, this is brand agnostics, this happens to any array, there's your physics. So the question now becomes, how can we redistribute the energy from an area where there's too much, which is underneath the balcony? How can we redistribute this energy from an area where there's too much to areas where there's too little, which is in the first couple of rows, and on top of the balcony? That's where we have too little. And the question becomes, can we somehow redistribute this energy and make it go to places where there is too little of it? Because we have too much, we see it in the section view, we see it in our measurements, we have too much underneath the balcony. We want to redistribute that to the start of our audience and on top of the balcony. Now, before we're going to look at solutions, you first need to understand, why is this happening? Why do I have a concentration of low mid energy under the balcony in this case? And why do I have too little in the start of my audience and too little on top of the balcony? Well, this is going to be a minor acceleration, but for those that attended some of our line trainings, our live trainings, such as a sound design and optimization course or the portable system deployment course, the live trainings, you might have seen a phase wheel at one point. Maybe not in our webinars or seminars, but maybe at one point in your career, you have seen a phase wheel. And a phase wheel basically tells you something about the interaction between two signals. Could be two sine waves, two correlated signals, two sine waves, whether it's volts or Pascal or pressure, but basically it tells you what happens when two signals interact with or without a phase offset. And when we're dealing with correlated signals, most of you will know that if we add two signals of the same magnitude with no phase offset, that we gain 6 decibels. And most of you also know that if you flip the polarity from one of these signals, that you get cancellation, which leaves about 358 intermediate phase values to play with. We're not going to explain that at great length, but this is the general progression. With 0 degrees offset, two elements that are equally loud, two signals that are equally loud, gain 6 decibels. By the time these two elements have been shifted with respect to each other by 55 degrees, you only gain 5 decibels, which is 1 dB less than you would have had with no phase offset. By the time you are at 3 o'clock or 90 degrees, you only gain 3 decibels rather than 5 or 6. And now comes an interesting milestone, because at 120 degrees, for two signals that are equally loud but with 120 degree phase offset, you don't gain anything, you don't lose anything. The level, the sum, the combined level, simply remains the same. Then we start to see what is known as destructive interference. Come 150 degrees, we actually start to see losses. Two signals that are equally loud but 150 degrees apart result in a 6 dB loss. And of course, 180 degree offset or half a cycle or polarity reversal will cause, in theory, will cause minus infinity. Then as you start to continue, level starts to rise again. It's still cancellation, but by the time you're at 210 degrees, 210 degree offset, you are back at minus 6 again. By the time you are at 240 degrees, which is 2/3 of a cycle, or 2/3 of a wavelength, which is 2 ways of saying the same thing, you're back at that critical milestone where you don't gain anything, don't lose anything. At 9 o'clock, you get the same as at 3 o'clock because the phase wheel is completely symmetrical. So with a 270-degree phase offset, you gain 3 decibels. By the time you're at 305 degrees, which is the conjugate angle of 55 degrees, you're back at 5 decibels of constructive interference. And once you've made your full revolution, completed a full revolution, I should do it for this, for you guys, full revolution, find yourself back at the top of the phase wheel. You're late by 1 cycle or early. Regardless, there's a 1 cycle offset. You're in phase, but 1 cycle out of time, so you gain 6 decibels. Those that are familiar with the phase wheel know this routine. But very often you run into the question to be coupled or to be not coupled, to be uncoupled. And basically, that's a binary question. And in order to appreciate that, let's look at the simplified phase wheel. When there is constructive interference, when there is addition rather than cancellation, you have to be in the green part of the phase wheel, where there is as little as 0 decibel summation when there's 120 or 240 degree offset, to as much as 6 decibels of summation with no offset altogether, 0 degree offset. When you're in this part of the pie, then you have constructive interference, you have summation, you're coupled. Whereas if you reside in the red part of the pie, where there's destructive interference, losses, rather than gaining something, we lose something. When you're in this part of the pie, there is destructive interference. Therefore, you are uncoupled. Okay? So it's a binary question. Am I coupled or not? Depends whether you live in the green part of the pie, which is 2 times larger, or whether you live in the red part of the pie, which is only 1/3 of the overall pie. And that means that 2 signals that arrive within 120 degrees, which is 1/3 of a cycle or 1/3 of a wavelength, as long as they arrive within 1/3 of a cycle, 1/3 of a wavelength, they are coupled and they will add in unison anywhere from 0 to 6 decibels. And that is what it takes to be coupled. And for 20,000 frequencies, these are 20,000 different times, because 1 kilohertz takes 1 millisecond to finish a single revolution. Therefore, 1/3 of a cycle is 0.33 milliseconds. Whereas 100 hertz takes 10 milliseconds to finish a single revolution, and therefore 1/3 of a cycle is 3.33 milliseconds. But the principle holds. 2 signals arriving within 1/3 of a wavelength, 1/3 of a cycle, 120 degrees are coupled and will add rather than subtract. So, with that knowledge in place, let's look at a wavelength. This is a single wavelength of an arbitrary frequency. Couldn't care less. Arbitrary frequency. Of course, 1/3 of it, if we chop it up in 3 slices, 1/3 of a wavelength is indicated by the orange arrow in the bottom of the screen. That's 1/3 wavelength. Now, if this were 125 hertz, give or take, 125 hertz, give or take, this might be 3 meters and change, which means that 1/3 wavelength would be about 1 meter. Sure, if you're 125 hertz. But if you're 1 kilohertz, then 1 wavelength is 34 centimeters, and 1/3 wavelength is about 10 centimeters, give or take. And in our map prediction, where we see the problem right now, happens to be very pronounced at a frequency of 200 hertz. Now, if your frequency of 200 hertz, then 1 wavelength is about 1.8 meters, and that means that 1/3 of a wavelength is about 60 centimeters. It's a little bit less, as we're about to discover. Because let's look at our example, let's look at our venue from the position underneath the balcony. This is the position underneath the balcony. We're observing our array, and the width of this orange arc, is 1/3 wavelength, which if you are 200 hertz, that is about 57, okay, about 60 centimeters. So the width of 1/3 wavelength is what is shown over here. And if you're able to appreciate this, then you should also be able to understand within a blink of an eye that if you're living underneath the balcony, that 12 out of 12 loudspeakers are coupled. That is to say, 12 out of 12 loudspeakers arrive within 1/3 wavelength or less. And that means that they all add. Sure, if you're living underneath the balcony, which is also where you happen to be perpendicular to the array as a whole. Remember, this beam, this concentrated energy, always runs perpendicular to the array as in its entirety. So if we do our cross once more, perpendicular 90-degree angle, you see that that's where you get the bulk of your energy, because at 200 hertz, that is where 12 out of 12 speakers are coupled. Sure, if you live over there. So how does that change if we move up the balcony? Let's go to our next position. It's a purely geometrical problem. When I'm living at the last row on top of the balcony, rather than having 12 out of 12 loudspeakers being coupled over there, I only have 9 out of 12. And that means fewer loudspeakers that are coupling at that point in space, and fewer loudspeakers are coupling ultimately translates into fewer SPL, because I'm not enjoying the mutual horsepower of all those loudspeakers. Geometry doesn't allow for it. So yes, if I live underneath the balcony, yes, but if I live on top of the balcony, I only get 9 out of 12. So how does that change when we go to the first row? Well, from the perspective of the first row, only 7 out of 12 loudspeakers. I did a polarity reversal on the numbers. Let me fix this, because that's an important, this should be a 5, okay? When I live in the first row, only 5 out of 12 loudspeakers are coupled. That's even fewer loudspeakers as on the balcony, let alone fewer loudspeakers as when you live underneath the balcony. And that's why I have less pressure in those first couple of rows. And the bulk I get when I live underneath the balcony. A little bit less when you live on top of the balcony, and even less when you live in those first couple of rows. It's a purely geometrical problem that we're dealing with. And if you have a geometrical problem, then you're dealing with time offsets. And the only viable solution for a time problem is a time band-aid, not EQ. EQ you use when you have a level problem, but we don't have a level problem. We clearly have a geometrical problem which translates into time offsets. And time offsets can rarely be fixed. A time problem can rarely be fixed with a level band-aid such as EQ. When you have a time problem, you need a time band-aid. You need a temporal band-aid to fix a time problem. And if you understand that, that basically eliminates gain shading, level tapering. All of those solutions are out of the picture, because gain shading, level tapering are all level band-aids which only work for level problems. But over here you have a time problem, you have a time of arrival problem, and that can only be fixed with the proper remedy, which is a time band-aid rather than a level band-aid. Now that we have a better understanding of the problem at hand, now we can start thinking about, well, how can I explore solutions? What would be a possibility for me to spread that beam which is currently too narrow? Well, if you would do it mechanically, one way of doing it is deploying the array not in the fashion shown by the blue picture, but in the fashion shown by the orange picture. Sure, if 200 hertz was the only frequency that I needed to be concerned with, of course, introducing more spread between the loudspeakers would also spread the beam at 200 hertz. Yeah, at 200 hertz, yes. So let's explore that option. Is this one mechanical way that would allow us to spread the beam which is currently too narrow? Well, that is something that we can easily investigate by not deploying our array in this fashion, but go to our layer management and deploy the array in this fashion. That array has overall more curvature, and if you have more curvature, then surely at 200 hertz, that beam will open up. So let's look at 200 hertz when we deploy the array like this. Well, there you go. Issue solved. 6 dB of variance front to back. You've spread the beam mechanically. And you can only do this if your program content consists of a sine wave, because 200 hertz is clearly not the only frequency that we're listening to. This might have improved the situation at 200 hertz, but it goes without saying that if we now go to one octave, 4 kilohertz, that the same mechanical deployment or mechanical articulation at 4 kilohertz is completely unacceptable. I mean, we're sending almost half of the loudspeakers are pointing into the roof. But yes, the situation at 200 hertz was improved if you do it like this mechanically. Goes without saying that this is not an option, because 200 hertz is not the only frequency to be concerned with. There's about 19,999 other frequencies that we need to be mindful of. This is just to show you that, this is your phase steering. This is Harry Olson, 9040. If you increase the curvature, if you open up your slice of pizza, of course, that beam opens up as well. And just to prove that, let's look at those two solutions side by side. On the left, we see our original design with 46 degrees of array splay. That is the angle between the top and the bottom speaker. And without any bells or whistles, we see that that beam is too narrow. On the right side of our screen, we have overextended our curvature. We have opened up the array all the way to 88 degrees, making that slice of pizza even wider, and it opened up the beam as was to be expected. But now all other frequencies, particularly mid and high frequencies, are pointing in places where you don't want them to end up. So the question becomes, how can we achieve the same effect, spreading the beam, without having to do it mechanically? Because clearly that's not an option. That's not an option because your waveguides end up pointing in the wrong direction as well. So then the question becomes, is it possible, as we're about to discover, is it possible to somehow do this electronically? But I still want you to appreciate why increasing the curvature of the array makes a difference. Because let's go back to this exercise. Still 200 hertz, okay, where one wavelength is about 60 centimeters. Now, at this position underneath the balcony, we had 12 out of 12 loudspeakers that were coupled over there. However, because of the increased curvature of the array, now at that same point in space, only 10 out of 12 loudspeakers are coupled. These are fewer coupled loudspeakers, so surely SPL drops. On the balcony, there is little or no change. Even with the increased curvature of the array, on the balcony, still 9 out of 12 loudspeakers are within that 120-degree phase offset that constitutes coupling. The biggest change is in the first row. In the first row, previously we had only 5 out of 12 speakers that were coupled over there, whereas now, after increasing the curvature, we suddenly have 7 out of 12 loudspeakers that are coupled over there. And let's compare the previous pictures to the current pictures side by side. On the left, we see our original solution with the array deployed as intended, resulting in 12 out of 12 loudspeakers being coupled underneath the balcony. If we increase the curvature, making the slice of pizza larger, we spread the beam mechanically, we reduce the energy underneath the balcony, because underneath the balcony, only 10 out of 12 loudspeakers are now coupled. If we go up to the balcony, very little has changed. Okay, it remained 9 out of 12, 9 out of 12. But the biggest change is, of course, in the start of the audience. In the start of the audience, we've essentially gained the 2 loudspeakers that previously were contributing to the position underneath the balcony. So we ended up mechanically redistributing the energy from an area where there was too much to an area where there was too little, mechanically. And like I said before, if 200 hertz is the only frequency of interest, this would work, except that it's not the only frequency of interest. So we don't get to do this mechanically. However, LMBC can fix this for us, because for those that work with subwoofer arrays, if you want to turn a straight subwoofer array into an arc, you typically use delay tapering, increasing the delay from inside to outside. Well, we could also consider doing that with our array. We could use electronic delay and give our loudspeakers a virtual push to their expected position in space where they would have lived had we actually increased the curvature of the array and turned it into a larger slice of pizza. Now, if we were to do this with pure delay, by which I mean electronic delay applied to each loudspeaker for all frequencies, then that's the last time that they will let you try doing that. Because if you start to delay loudspeakers individually within a line array, okay, you're setting the table for shed loads of things to go wrong. So unlike subwoofers, which only operate in 1 or 2 octaves at most, we do not get to do this with line arrays. We cannot use pure delay in every individual loudspeaker, delaying all frequencies. The challenge becomes not to do this with electronic delay for all frequencies, but to do this by means of frequency dependent delay. And in Galaxy, the way to achieve frequency dependent delay is all pass filters. So what LMBC does is that it virtually increases the curvature. It transforms the shape of the array electronically only for those frequencies where it needs to happen. And those frequencies where we want to increase the curvature, which we cannot do mechanically, by means of all pass filters, which allow us to introduce frequency dependent delay, that solution, which is a time solution to a time problem, that solution should only take place, for today's example, between 100 hertz and 1 kilohertz, where the beam is too narrow, sending too much energy underneath the balcony. We don't want to mess with any of the frequencies above 1 kilohertz because there's no reason to do so. We already have the desired beam width, as we saw, and we have no reason to do anything below 100 hertz because we already have the desired beam width. So it would never be possible to fix this with electronic delay, delaying all frequencies equally applied at different amounts to every element in the array. However, carefully arranged all-pass filters will allow you to electronically increase the curvature of your array, spreading the beam electronically, but only for very select frequencies, So before we're going to talk about how to do that, I'm just going to show you the end result, which means that this solution, the mechanical steering, which is not an option, I'm going to hide that one, and I go back to my original design. There is the Leopard array, which works for all frequencies except for that decade around 200, 250 hertz. Now, how to do this, we're going to finish with at the end of today's webinar. First, I want to show you the end result, which means that I go to my settings, and then 8th option from the top is my low mid beam control. I've already dialed in all the parameters. The only thing that I'm going to do is I'm going to take the status out of bypass. I'm going to take it out of bypass. I'm going to close the dialog. LMBC is now inactivated, and let's look once more at that same frequency range, 1/3 octave, 200 hertz, and let's look what happened after we turned on the LMBC, which will now spread the beam electronically only for those frequencies. This is with the LMBC engaged, and you clearly can see that the beam has been spread. Whereas if we turn off the LMBC by putting it in bypass and do another prediction, this was a departure point, this is without LMBC. Notice the difference? In order to make you appreciate this more, why don't we put those two side by side, and look at them in our keynote presentation. Because here you see the mechanical solution with the overextended coverage, the overextended curvature, 88 degrees, which opens up the beam, sure, at 200 hertz, 200 hertz, but now points the waveguides, the ribbon emulation manifold, the REM waveguides, completely in the wrong direction. That is not acceptable on the left side. However, notice that on the right side, with LMBC set to beam spread, we almost get the same shape. It's almost a carbon copy of the same shape, but the loudspeakers are still pointing in the right direction. And that's what LMBC did for us. It spread the beam using all-pass filters, which introduce frequency-dependent delay. It spread the beams for those frequencies where the beam needed to be spread. And that's what LMBC does. And this application is known as a beam spread. Now, how to do that, we will discuss later. What is, of course, interesting is now to compare our measurements. Because in the top, without LMBC, we see our three original measurements. White being the measurement in the first row, blue being the measurement underneath the balcony where we have this concentration of low-mid frequencies, orange being the microphone on the top of the balcony. And we clearly see that those transfer functions do not show a similar trend. Now, with LMBC engaged, suddenly we get the progression that you see in the bottom. Notice that these three traces have now converged and are in much better agreement with each other. And that means that all frequencies, including the ones at low mids, where the beam was too narrowed, all those frequencies are now back at attenuating by the same amount over distance, meaning that tonality is preserved over distance. And the reason that this works so well is because we used a temporal band-aid, a time band-aid, to address a time problem which is determined and dictated by geometry, rather than trying to do this with EQ or trying to do this with gain tapering or level shading. Because gain tapering, level shading is only successful if there's isolation. If there's no competing loudspeakers in the same area, then EQ, then gain shading is a viable solution. But if there's no isolation, if there's no separation, then you will not be able to make the most out of EQ. So in order to make you appreciate that, let's go to our properties and let me show you only the top and the bottom loudspeaker. Okay, so here's what I'm going to do. I want to only see the top and the bottom loudspeaker, which means that I'm going to start with the bottom loudspeaker. I'm going to solo it. I'm going to turn on the master solo, applying close. Let's take a picture of that bottom loudspeaker. So that is the contribution of the bottom loudspeaker at the fourth row, okay, only the bottom loudspeaker. Let's look at a transfer function of this guy, okay? So we go to our transfer function. Let's make a picture of this guy, auto set delay. Let's, I don't want that one. Let's store this and call it, okay? Let's call this bottom speaker solo at VBOT. So this is the bottom speaker in the fourth row at the start. We've stored that, okay? There it is, okay? We can recall it and compare it later. Now, rather than looking at the contribution of the bottom speaker in that same position, I motion that we don't solo the bottom speaker, but we solo the top speaker, okay? And see what the top speaker is still sending to that fifth row, and make you appreciate that you cannot fix this with EQ or with gain shading or with level tapering. Because if we now look at our top speaker, which is now indicated by the black line, then you see that the top speaker in the fourth row, if we increase our scale a little bit, okay, that the top speaker in the fourth row is less than 6 decibels, is within 6 dB or less with respect to the loudspeaker that is actually facing in the direction of the first row. So there's little or no isolation, as we call it. And if there's no isolation, then EQ becomes futile. We do not achieve isolation, for which it takes 10 decibels at least. Okay, there's no isolation between these two loudspeakers below 1 kilohertz. Okay, it's not until you go higher than 1 kilohertz that the top loudspeaker no longer exists in that first row, because there is 10 dB of isolation or more. Sure, above 1 kilohertz, that top loudspeaker no longer exists in the first row. But we're talking about frequencies. We're talking about frequencies that live over here. This is our problem area. And in that area, these loudspeakers are still very much competing with each other. And when they're competing with each other, then gain tapering, EQ, all of those things will become less and less of a viable solution because there is no isolation. Okay, so hopefully that allows you to appreciate that more. Okay, so there you have an example of the beam spread. Now we're going to look at a different example, which is the beam tilt. And then we'll finish today with how do I set this up. So here we see a larger environment, clearly a larger environment. This is an area which is over 100 meters deep, left to right, over 100 meters deep, left to right. And our array is about 18 meters up in the air. This is something that you would expect outside during a large-scale sound reinforcement event. And again, you know, for mid and high frequencies, it's point and shoot. Just send the sound where you want it to go. At 2 kilohertz, I'm perfectly happy. I'm doing a 100-meter stretch, starting at 10 meters. I'm doing a 100-meter stretch with 6 dB of level variance. So at 2 kilohertz, I'm perfectly happy. All is fine because now we're in the regime where it is point and shoot. But what happens if we now start to look at our low mid frequencies? This is 125 hertz. And at 125 hertz, notice what is happening. Again, we see that very narrow concentration of energy. We see that very narrow concentration of energy. The overall orientation of that concentrated low mid energy is again perpendicular to the array as a whole. And like before, we're overshooting the start of the audience and we're doing a nosedive before we cover it all the way up to 100 meters. And inside, room gain might be beneficial, might alleviate some of this of these issues. But outside, where there is little or no room gain, where you are on your own, where you are basically in near anechoic circumstances, outside, there's no room that decelerates this level loss over distance. So now the question becomes, can we use LMBC in a similar fashion to keep the beam from doing a crash landing over here around 55, 56 meters, doing a crash landing over there, and can we somehow tilt the beam and send it more towards those distant spectators? Because it goes without saying that 125 hertz are not like entirely unimportant frequencies. So is there somehow that we can tilt the beam, sending that energy to the distant spectators? And the answer, again, is twofold. Sure, we could do it mechanically, okay? If we were to pivot the entire array, around the base of the array, if we were to pivot the entire array around the base, okay, then we would be able to steer that concentrated beam of energy at 125 to steer that to the distant seats. Goes without saying that the price, the trade-off that we pay for that solution is unacceptable. But just to entertain you, what if we were to deploy the array like this rather than that? Okay? I know that you know that this is not a viable option. I just want you to appreciate that if we were to deploy the array like this, that the same concentrated amount of energy now goes where it needs to go, which is to those distant seats, preserving introducing a much gradual drop in level over distance. The trade-off is that about 60% of your waveguides are pointing in the wrong direction. So again, we cannot do this mechanically. For obvious reasons. And the question becomes, is there a way that we can do this electronically? Is there a way that allows us to somehow transform our array from the blue shape into the orange shape? Because mechanically, it's clearly not an option. Yes, electronically. But for reasons that we discussed before, we cannot do it with pure delay, delaying every loudspeaker individually, but delaying all frequencies, because that would completely mess up everything else. So also over here, the challenge becomes, Is it somehow possible to use frequency-dependent delay by means of all-pass filters and change the curvature of the array only for those frequencies where it needs to happen? And the answer is yes, with help of LMBC. But rather than doing a beam spread, this is known as a stair up. So I'm going to hide this layer. We go back to our original design. Okay, this is currently where the frequencies are going, which is doing the crash landing in the middle of the field, never making it to the end of the audience. Now we're going to turn on our LMBC. Okay, we're going to turn on our LMBC, which now spans across 2 Galaxy devices because it's an 18 loudspeaker array. And I will explain you how to do that across 2 Galaxy devices. There's one living on address 10. There's one living on address 11. Okay, let's see how it changes when we turn on LMBC, instructing it to do a steer up. Same frequency range. Notice that without re-aiming the loudspeakers, that beam is now going in the same direction as we achieved previously with the mechanical steering of the array. Except that now the mid and high frequencies, which were very much going where we wanted them to go in the first place, are still going there. And only those frequencies where the beam was doing a crash landing have now been pointing in the right direction. And in able to make you appreciate this, let's do a comparison of before and after, because doing it electronically only for select frequencies, as we discussed in the keynote, allows us to achieve the same effect like before that you would have achieved with mechanical steering. So in the top, we see our original problem, 1 octave, 125 hertz. We see that without any steering, mechanically or electronically, that this concentrated beam of energy is doing a nosedive in the middle of the field, overshooting the start of the coverage, never making it to the end of the coverage. We also saw that if we tried to do it mechanically, by changing the overall orientation of the array altogether, that we will achieve to send the sound where it needs to go. And hopefully everybody see that that resulted in a steer up, in a up angle steering of this lobe of energy. Okay, we managed to introduce about 6 degrees of up steering, but now the waveguides are pointing in the wrong direction. Whereas if you do it with LMBC, then the waveguides are still pointing where they need to go. Our ribbon annulation manifolds are still pointing where they need to go. But notice that as far as 125 hertz is concerned, the low mids, that the picture with the mechanical steering versus the picture with LMBC are virtually indistinguishable from each other, like before with the beam spread. Why? Because for the same reasons, you fixed a time problem caused by geometry, you fixed a time problem with a time band-aid, not EQ or gain tapering or level shading, because at 125 hertz, okay, you are still in the shared custody of each and every one of these loudspeakers. If I were to show you one Leo and one Leo alone, okay, never mind which one, okay, let's do a single Leo. Let's solo the top Leo, turn on the master solo, look at that same frequency. Then you will notice that at this frequency, one of these loudspeakers is still virtually omnidirectional. So wherever you go at 125 hertz, there's no isolation. And in the absence of isolation, EQ, gain tapering, level shading doesn't work. You have a time problem, you need a time band-aid. That's what's known as a steer up. Which brings us to the, how does that change the transfer functions? Well, let me go to the map and show you where the microphones lived that I used to do these measurements. Okay, here we see the microphones. There is one living in the start of the audience over here, which is my V bottom. This is what I called on-X, and that is V top. Same labeling as we saw before. And then we can look at our transfer functions with and without the LMBC steer up. So in the top, we see the result before the steer up, and there's several things that I would like to point out. Notice that in the start of the audience, we have considerably more 63 hertz. Notice that also in the in the end of the audience, which is the orange line, we have substantially less of these frequencies because the beam is doing a nosedive somewhere halfway through the audience. So we wanted to steer that beam towards those distant spectators. And we ended up managing to do that when we turn on the LMBC with the 6-degree steer up. Notice that these three measurements are now in much better agreement. Notice also that for other frequencies, they are in much better agreement because we steered the beam up. And with the beam steering, like before, those traces are in much better agreement with each other than without the beam steering with the steer up. And this is what you would also observe in the field when you were to measure this. So there you have the two ways that you can use LMBC, which is your steer up and which is your beam spread. So how does that work in Compass? Well, it was introduced around 2018, and there are several things that you can and that you can't do. So when we finish with how to do this, then we're going to talk about what you can and can't do. It goes without saying that all loudspeakers need to have the same drive signal, need to have the same polarity. That goes without saying. You also need to apply LMBC for making any EQ choices because LMBC redistributes the energy from areas where there's too much to areas where there's too little. And of course, that will affect the transfer functions in those positions. So you want to do LMBC first before you choose, make any choices with regarding to EQ. Gain tapering can make LMBC ineffective. Yes, because if you build in a level offset, then you do not exploit the time band-aid that you just applied. So that would be very ill-advised. Also, in terms for those that array their, that zone their arrays to compensate for air losses below 1 kilohertz, okay, you want to treat your array as one big system, which means that below 1 kilohertz, you don't want to use any different EQ at those frequencies. Any EQ applied below 1 kilohertz should be applied to the array as a whole. Whereas above 1 kilohertz, when you divide your array in zones, sure, you can use shelving or U-shaping, in our case, U-shaping or parametric EQ to correct your high frequency losses within reasons. When you do a beam spread, you will not get optimal results when you try to spread more than 95 degrees. So that's ill-advised. And the same is true with the steer up. The steer up is not optimal when the array splay, which we'll discuss in a second, when the array splay exceeds 45 degrees. Our recommendation is to wire one element per galaxy output, which means that the most you can do on a single galaxy is 16 elements wired individually. If you insist, you can also do 2 elements per output, in which case you need at least 12 loudspeakers. You need at least 6 times 2 loudspeakers for it to work. The price that you pay for 2 elements per output rather than 1 is that you will see the onset of grating lobes. You will see spurious side lobes shooting in directions that you typically do not want. That being said, it is the second preferred solution. The first preferred solution is 1 element per output of the galaxy. To protect you from overdoing it, Compass software has been designed to not allow for invalid or non-optimal configurations. So occasionally it will give you a warning. It will give you a warning telling you that what you're about to do might be ill-advised. So let's look at how to implement this. For those that watch the Introduction to Compass webinar, low mid beam control can be found on its own top in the top-based control software, which you will find under settings. Now there's a lot to see here, so let's go through it one step at a time. Within this top for a single galaxy, I can introduce LMBC for as much as 4 arrays. Let's look at one instance of an array. These are all the settings that are relevant to apply LMBC. So the first thing that we can do is give our array a logical name so that we know that that's the array that we're dealing with. Of course, as you already saw me do in map, I can bypass the array or I can take it out of bypass if I desire to do so. And then under control type, we have to decide whether we want to do a spread or whether we want to do a tilt. Okay, that's where you choose your strategy. So in the second example, we did a steer up, whereas in the first example, we did a beam spread. In the next option, we have to decide how many elements per output. Our recommendation is 1, in which case you need at least 8 loudspeakers. You can also set it to 2, in which case you need at least 12 loudspeakers over 6 outputs. So that's where you set the number of elements per output. Then the Galaxy device needs to know where the top speaker in your array lives. So you have to wire every loudspeaker individually. Our recommendation is top to bottom, loudspeaker at the top on output 1, and then all your way to the bottom, consecutive outputs. Because it needs to know where it has to live. Where does the top loudspeaker live, and on what output of my Galaxy does it live? In order for the LMBC algorithm to work, it also needs to know how many elements live in your entire array. So in the first example, we had 12, and in the second example, we had 18, but I only have 16 physical outputs in the Galaxy. So how does that work? We'll get to that last. And finally, I need to know which element lives on output number 1 or whatever output I choose. Well, if the top element of your array lives on physical output number 1, then this is how you would set it up. On physical output number 1 lives the top element of my array. And then, of course, for the LMBC algorithm to work, it needs to know which product are you using. LMBC is only supported on Leo family products, which is Leo, Lion, Leopard, and Lena. And that's where you set your product type. And then we get to the interesting part is, what is the array splay? Because the array splay will determine how much the beam is spread or how much the beam is tilted. Fortunately, this requires no math whatsoever because the array splay is shown at all times in the top right corner of your flown loudspeaker system properties in MapXT. So here we see the flown loudspeaker properties in MapXT, and notice that in the top right corner, that's where it says my array splay, which it did for the beam spread using the Leopard loudspeakers, but you will also find it there, as we're about to discover, when we did the steer up. You will also find that value over there. That is the value that you want to copy into that field, which will allow the LMBC algorithm to determine the amount of spread that is required or the amount of steer up that is required. Those are all the settings that you need to know. And then finally, there is a field which will bring up some comments depending on what you do. When you're trying to do which is something which is non-optimal, that will turn to red. That will show you a warning. And we can look at several of those warnings. Wow, I'm running a little bit over time. Sorry, this is a very involved topic. So let's go to our beam spread first. Here we have our Leopard. Let's look at the Leopard and how it's been wired. So let's bring up the dialog. Okay, let's bring up the dialog. Notice that all the individual Leopard loudspeakers, 1 through 12, have all been connected to the Galaxy that lives on address 12. Okay, that's what we use in a SIM ecosystem. Okay, this Galaxy lives on address 12. But other than that, that Leopard number 1, it's the top of the array, has been connected to physical output number 1 of that particular Galaxy. The Leopard that lives beneath it has been connected to output number 2, and then 3, and then 4, and then 5, and then 6, all the way to 12. So each loudspeaker is wired individually, top to bottom. If I bring up the processor, now notice this, the 46-degree array splay. That is the value that, of course, we want to memorize in this application. So now we go to that particular processor, okay, and notice that I could call this Leopard number 1, okay, which would be the top guy. Then this would be Leopard number 12. That would be the bottom guy. and all the intermediate leopards would live in between there. That's how they would be wired, except for the bottom 4 channels. And you would see something similar in the compass control software. So that is how these leopards have been wired. Now we go to our low mid beam control. We're using the galaxy that lives on address 12. And we're using one array which I've called leopard 46 degrees. I put the 46 degree there to remind myself that the array display of this array is 46 degrees. We're doing a beam spread with 1 element per output, not 2. Watch what happens if we were to do this with 2. Okay, I'm going to show you that in Compass. So let's keep this at 1 element per output. Then I need to instruct the low mid beam control dialog where the top element lives. Where does element number 1 live? The upper loudspeaker. Well, the upper loudspeaker of my 12 speaker array, 12 number of elements, 12 speaker array, number 1 is connected to output 1 of that galaxy. Okay? And then it knows that 2, 3, 4, 5, 6, all the way to 12 live underneath it. Of course, I also need to tell it, oh, there we have, M series has been added. Awesome. I also need to tell it that, what is the product that we've been using? Well, we're using leopard. And then finally, that parameter, what is the array display? Well, that's the value that we got from the flown loudspeaker properties. That's the 46 degrees. That's all the parameters that I need to introduce. We're trying to do a beam spread with 1 element per output. The top element, element number 1, lives on output number 1 of the galaxy. I'm using 12 elements in total, which consist of leopards, and I need a 46 degree spread. If I now take this out of bypass, do a prediction, then we get the desired result. Okay? Provided that I turn on all loudspeakers, or that's to say that I don't solo one loudspeaker. And then you get the desired result. So, okay, that's what happens if you make an operator error, because I did not apply my change. Okay, apply and close. Let's try that again. So that is the result that you would expect to see with the beam spread. Now I would like to go to the steer up, because over here I am using an array which consists of 18 loudspeakers in total, but I only have 16 loudspeakers on a galaxy. So if you pay close attention, you can see that Leo number 1 is wired to output 1 of the galaxy that lives at address number 10. And we keep doing so all the way until we get to the 16th Leo, which is connected to the same galaxy at address 10, output 16. But I have 2 more Leos in this particular array, which are 17 and 18. And these 2 loudspeakers are connected to the next galaxy. So I have 18 loudspeakers spanned across 2 galaxy devices. The first 16 live on the galaxy on address 10. The second 2 live on the galaxy on address 11. The other thing that you might want to take note of is the array display of this particular array, which is 24 degrees. So let's go to the keynote and see how you deal with an LMBC solution that spans across multiple galaxies. Okay, over here we have 18 elements. After all, our Leo is 18 elements tall. But I only have 16 physical outputs on a galaxy device. So notice that the first 16 loudspeakers of the Leo array are wired through output 1 through 16 of galaxy number 1. And then the bottom 2 Leo loudspeakers, 17 and 18, are wired to output 1 and 2 of the next galaxy, which is galaxy number 2. That means that every loudspeaker is still connected to a unique output, but the total number of elements spans across 2 galaxy devices. So how would that look in Compass or in MapXT? Well, on one galaxy, top to bottom, I have Leo 1 through 16, which are the guys that live over here. And then on the next galaxy, I have Leo 17 and 18 connected to output 1 and 2 of the next galaxy. This is one way of doing it. So I have 18 loudspeakers, across 2 galaxy devices. So how does that look in MapXT in the LMBC dialog? Well, in the LMBC dialog, it would look like this. For one galaxy, the one that lives on address 10, we are using 18 elements, okay? But the top speaker of those 18 elements, number 1, lives at output 1 of that particular galaxy. And then, of course, we have our 24-degree array splay, which we copied from the previous dialog. Now, what is happening with the remainder 2 Leos? They live on a different galaxy, which lives on address 11. I need to tell map that it's the same amount of speakers, 18. But the top speaker in the 2 Leos at the bottom, the top speaker is, of course, not number 1 at the top. This is number 17. This is the second to last speaker in the bottom, which lives on the physical output number 1 of that galaxy. And that is how both map as well as compass know how to span the LMBC solution across multiple galaxy devices. In all instances, we're using Leo. That much is clear. Of course, the array splay should be identical. That is clear. Same number of elements. That is clear. But in the upper solution, the top element lives on output 1 and then all the way down to 16. Whereas on the second galaxy, it's only the second to last loudspeaker and the last loudspeaker that live on output 1 and 2. All of this is, of course, also documented on the Meyer Sound website. That is how you can span LMBC across multiple galaxy devices. So let's see that happen in MapXT. Okay, notice I already said this, the first 16 loudspeakers live on the first galaxy, whereas the second 2 loudspeakers live on the second galaxy. If I were now to bring up my LMBC dialog, which lives over here, notice that on processor, which lives on address 10, we have 16 of our 18 loudspeakers with the top speaker on output 1, and then the remainder 2 loudspeakers live on 17 and 18. Those are the remaining loudspeakers. They live on the first 2 outputs of our second galaxy device. And that's how you span across multiple galaxies. All that's left to do is take the solution out of bypass, and then you can see before and after. That is how it works in MapXT. So how does it work in Compass? Well, if you understand it in MapXT, then you will also be able to understand it in Compass. Because in Compass, the dialog is functionally the same, okay? In the first solution, where we had my leopard array, we did a beam spread. We had 1 element per output, okay? The top element, number 1, lived on output number 1 of that galaxy. We used 12 in total, and the product that we used was leopard, okay? And the total array splay was 46 degrees. If I now take it out of bypass, that would now be working. And in my overview, I can now see those all pass filters, okay? That's where they are, okay? Here you see that we're using the LMBC, okay? That's where they live. And that's how you use frequency-dependent delay, in this case, to spread the beam. And by extension, you could do the same for the steer up, in which case you would not choose a beam spread, but you would use a steer up. So the only thing that is shown over here and not shown in MapXT is that now we get to talk a little bit about that comment field, okay? That comment field that shows you what is going on over there. We're using outputs 1 through 12 Okay, and then over here it says fill system APF. What is that? Okay, purportedly with a frequency of 210 hertz and a Q of 0.64. Because the only thing that we haven't talked about is what is the trade-off for using LMBC. What is the trade-off for using LMBC? Well, this is the trade-off. Let's go to the settings and let's disable LMBC. I'm going to disable LMBC. Okay. And let's take a measurement of our array at that position underneath the balcony. Okay. Which is my second microphone. So let's go to the microphone, which is on axis, and let's get a picture of the array, set our delay, store this. Okay. And let's call this pre-LMBC. Pre-LMBC, and let's put that in memory A. Okay, so that's what the array looks like without LMBC. Now we go to our settings, low mid beam control. Now we're gonna enable our low mid beam control. Notice that over here, we also get the same remark. It also tells us over here that, okay, outputs 1 through 12 are now using LMBC. That means that you need an all-pass filter, but we don't know what the reason is for that all-pass filter. So we're almost there. We're almost finishing today's webinar. So let's look what happened after we turned on the LMBC. Okay, so there we go. I must have made an operator error. Although I do see a change, okay, so clearly I'm making an operator error. There we go. There we see the result. Now, who can tell the difference between before and after? The red trace was our array prior to turning on the LMBC, whereas the blue trace is the active measurement showing us post LMBC. So this is pre and this is post. We see less energy underneath the balcony. This we already knew, but now you see the price that you pay for using all pass filters, which is that due to the all pass filters, we have gained a wraparound, a phase wrap, because that's the price that you pay for all pass filters. So we have a little bit of more phase shift. This is the trade-off that you pay for using LMBC. That being said, somebody questioned, do you take a performance hit in terms of latency when you resort to LMBC? And the answer is no, because when you use all-pass filters, unlike FIR processing, finite impulse response filtering, you do not get additional latency. So you get to use the steer up and you get to use the beam spread. The trade-off is an extra wraparound in your entire system, which wasn't there before. It's ultimately up to the user to decide what you prefer more, using LMBC at the expense of an additional wraparound, or not using LMBC, saving yourself an extra wraparound. That being said, this wraparound, which now lives in our Leopard system, does not live in my Ultra X20 front fill or in my Ultra X40 infill, which has a phase trace that comes from the same phase curve family as Leopard. If you want to know more about phase curve families, be sure to watch our product integration webinar. And that means that before I engaged LMBC, my Leopard array and my X40 infill or my X20 front fill, they were phase compliant. They had the same phase response. Whereas after applying the LMBC, the phase response of my Leopard array has now changed in exchange for spreading the beam, but it also means that that array is now no longer phase compliant with the front fill. So now we use product integration and delay integration to make all those loudspeakers phase compliant once more, and we end up breaking it again. Well, don't panic, because the dialog, the LMBC dialog, is showing exactly the remedy that you need to apply to fix that. Because notice that it says if you apply an all-pass filter, to the output or any loudspeaker that is not part of your Leopard array, if you apply an all-pass filter, using these parameters, which show you the corner frequency and the bandwidth of the all-pass filter, then your X20 or your Ultra X40 will once more be phase compliant, even when using LMBC. We see a similar dialogue. We see a similar dialogue in Compass, telling us as well that in order for your fill loudspeakers to remain phase compliant after using the LMBC, this is the all-pass filter you need to apply to the outputs containing fill loudspeakers, those outputs that are not part of the leopard array in this case. So 200 and let's say 210 hertz with a Q of 64. So for all I know, for the sake of simplicity, for all I know, my front fill, okay, lives at output 16. Okay, my front fill lives at output 16. So I go to my output processing, I go to my front fill, I go to the top all pass. There's 3 all pass filters to use. I go to any one of those. I make the values the same, 210 with a Q of 0.64 as suggested by my dialog. I take it out of bypass, and that will make sure that that front fill is once more phase compliant with the leopard array that now uses LMBC. That corner frequency is a recommendation. In the field, when you're calibrating the system, when you're commissioning the system, you might want to measure at the spot where your array and your front fill meet each other at the same level, and you might find out that as you actually start to measure this, that this all-pass filter might need a little tweaking. But this is the ballpark estimate, okay? This is the ballpark estimate to make it completely solid. You might want to validate this, and then you will discover that this guy might need to drift a little bit, but okay, we're talking only about a couple of dozen hertzes at most. So that concludes the how to apply LMBC. Everything that you need to be mindful of will be shown in this dialogue. Now, what happens if, let's say, rather than using 1 element per output, I use 2 elements per output? Now, in Compass, you get a dialog which says whenever you use 2 elements per output, grading lobes will occur, okay? They will not be deal breakers, but using 1 element per output is the preferred solution. So that's one of those instances where you get a warning that you're trying to do something which is ill-advised. What if I try to, do a value which is, very 99? I'm trying to force an error. So what if I try to spread too little? Well, then it says, this is not an ideal solution. This is not recommended. This is not optimal. So you get an error. Not to mention that our leopard array is, of course, not 10 degrees, but 46 degrees. So depending on what you're trying to do, it will throw you a warning and say, no can do. I think that pretty much concludes how to use LMBC, why to use LMBC, what you will gain, what the trade-off is. Trade-off is an extra wraparound, no latency, extra wraparound, which you can easily overcome by using the recommended all-pass filter in all remaining fill loudspeakers except for those that use LMBC. So what would be the normal order of operation? You would first set up your product integration. That goes without saying. You want to make sure that all your loudspeakers, no matter which generation they're from, feature the same phase curve. So you would first set your product integration, okay? Then you would set your LMBC prior to calibrating, because LMBC changes the way your transfer functions look. So then you set your LMBC, okay? And now you can start calibrating your main PA as usual. By the time you're about to mate a fill loudspeaker, such as a front fill or an infill, to your main PA, you will suddenly discover that even though they're no longer, even though you use product integration and delay integration, you will discover that suddenly that front fill, for reasons that we just discussed, is no longer phase compliant because of LMBC. And all that's left to do is to enter this global all-pass filter to those outputs, and that will make sure that post using LMBC, post enabling LMBC, that all those loudspeakers are phase compliant once more, and then you continue with your calibration practice. Okay? And that is the implementation of LMBC. And as I like to say, choose your poison. Okay? It's up to the user. It's icing on the cake, if you will. It's icing on the cake, and it's up to the user to use LMBC at his or her discretion. Okay, I accidentally stopped sharing my screen because that pretty much concludes the end of LMBC, which means that I'm happy to take a couple of more minutes to answer any of your questions. Please raise your hand and let me know what you would like me to answer. See, a lot of you guys have been asking questions during the call, but without raising your hand. So let me, okay, so how much punch definition will we lose? Well, not more or less than you would resort to the mechanical solution. If you increase the curvature of your system, okay, if you increase the curvature, open up your slice of pizza, then there will be more time smearing. And if you do it electronic, you will also get more time smearing. So I fail to see how that would affect punch and definition. The other thing that you might notice is because for the frequency range of interest, the beam is narrower. And because the beam is narrower, your direct to reverberant ratio is typically higher. And of course, if the direct to reverberant ratio is higher, it sounds more direct because you have more direct than reverberation. Now, if you open the beam up, then of course the directivity factor goes down. So your direct to reverberant ratio becomes a little bit worse. And you might perceive that as sounding less indirect, but at least now it sounds equally indirect or equally direct for everyone, okay? Because everyone is experiencing the same tonality. Some feel that it got worse with the stir up because we need more 60 hertz to keep up with the subwoofers. I could also turn your argument around and say, now we have good coverage from the main PA, but too much of those frequencies coming out of the subwoofers, then you need to think of ways how you can decelerate your low frequency content, your subwoofers, how you can decelerate their level loss over distance as well. Because we just fixed something, and now the question becomes, are we willing to give up on that solution just to keep up with the subwoofers? There's no wrong or right, but you could also start thinking about how can I decelerate my subwoofers from front to back. So that remains to be seen. Does LMBC affect overall system latency? No, because it doesn't use something like FIR. It uses IIR filters. It uses all-pass filters. Can we choose how many degrees we tilt? Well, you can play with that value. The erase play is the base value that allows you to either introduce a given amount of spread or a given amount of tilt, but the LMBC algorithm will derive that from the erase play value that you introduce. So you can tweak that, but tweak it in an informed manner. Okay, do it in an informed manner. Do not start tweaking that a great deal because the entire LMBC algorithm is based on the erase play, which you can get from your flown array properties. How decisively the 46 degrees are necessary in the first case? Again, similar reasons. You can tweak that value to your liking, but do it in an informed fashion. If we have a combination of Leo with Lion as downfill, for example, 12 Leos and 2 Lions. Okay. If the ratio of major elements to minor elements, so let's call our Leo the major element, let's call our Lion the minor element. If the ratio of major elements to minor elements is overwhelming, let's say 5-1. So for every line, I have 5 Leos, okay? Which means that I have 10 Leos or 6 Leos for every lion. If it's a high ratio, you can think of those bottom 2 lions and designate them in LMBC. You can designate each line and pretend for it to be a Leo. So if you have 12/2, Then on outputs 1 through 12, you would have your Leos, and on output 13 and 14, you would have 2 lion pretending that they are Leos. But only if you have an overwhelming ratio. That is, if you have anywhere from 5 to 6 times more Leos than you have 2 lions. Is the quality factor, the Q value for the global all-pass filter, always 0.64? I don't know. I don't know. Very often it isn't, but I'm not prepared to say whether it is so at all times. How the size leaves the 24 degrees in the second case, same story. Okay, that is the initial estimate. Tweak it at your own discretion, but do it so in an informed way. Of course, if you use all-pass filters to spread the beam or steer the beam, you do not get latency, but extra phase shift translates into extra group delay. Sure, but these loudspeakers already have notorious little group delay to begin with. Again, that is up to you. Try it out, and try it out. Like we say, it's icing on the cake. Try it out. Can you give us some kind of recipe for setting the all-pass filter for beam steering with a random processor, which allows us to do it? No, I cannot, because this is a Meyer Sound webinar, and this is a feature of a Galaxy device. So if you want to do this with a different processor, then that is something that you need to figure out. But the transients will not play at the same time. They will lag with angles display at the same time. Only the phase relationship changes. I fail to see that, Raphael, because either the loudspeakers are physically more distant or either the loudspeakers are electronically more distant. So I fail to see. I'm not agreeing with you at this point. Okay, and then Kaylin says, thank you. So are there any questions at this point? If not, this has been a dense webinar, but nonetheless, thank you very much. And hopefully you will join us next Wednesday, that is to say this Wednesday, for another Meyer Sound webinar. And tomorrow, my Spanish fellow Meyer Sound instructor, Ramicio Ramirez, also known as Magoo, is going to do the same webinar once more, but this time in Spanish. And of course, a recording of today's webinar will be available very shortly on our Thinking Sound YouTube channel. And that means that to those that were with us today, thank you very much for attending. Please stay safe, please stay healthy, and best to you and your loved ones. Bye-bye.